are division rings, while Zn is a division ring when n is a prime. So you see, from the above example, every integer less than n are co-prime to n when n is a prime. So that's why Zn is going to be a division ring when n is a prime number. HR is also a division ring, because if I take this non-zero element, I plus b, I plus cj, by a simple calculation, I can see that the inverse is 1 over I squared plus b squared plus c squared plus d squared times I minus b, I minus cj minus ck. So where I, j, k are defined before. Then our main part is talking about fields. What field is a commutative division ring. So it means every non-zero element in the set has a multiplicative inverse plus the commutativity of the second operation. So the following are rings. So you see Q, reals, complexes are fields. They are infinite fields. And the one which is finite field is Zn, where n is prime. The ring of integers is not a field because not every element in Z has a multiplicative inverse. So then I move to another definition. Sorry, Prof, I'm quick, so you can stop me at any time. So let me talk about the zero divisors. So this definition helps us to find the second notion of the title, which is integral domain. So a ring R is said to have divisors of 0 if we can find two non-zero elements in R with their product is equal to 0. So sometimes we cannot find any two non-zero elements in a ring R such that their multiplication is 0. So if we do have non-zero elements with this property, then we say that R has divisors of 0, or sometimes we call zero divisors. So for example, the ring Z6, so the ring of integers modulo 6, has divisors of 0. As we can see in Z6, 2 times 3 is equal to 0 modulo 6. Also 3 times 4. So this ring has divisors of 0. The following have no divisors of 0. We can see in Z, the ring Z, if we multiply any two elements, so the result is going to be 0 if and only if one of the elements is 0. That's why there is no 0 divisors. Q, R complex is the same. For Zn, if n is prime, then Zn has no divisors of 0. As we can see above from example 7.13, Z6, because 6 is not prime, so then this ring has divisors of 0. But in the case when n is prime, so Zn has no divisors of 0. As we said before, R with the second operation is just a semigroup. So it's not guaranteed that the cancellation law holds. So if our ring has no divisors of 0, so then the cancellation law holds. Otherwise, the cancellation law does not hold. So let's give a simple proof of this theorem. So suppose R has no divisors of 0, and take 3 elements in R such that A is not 0 and AB equals AC. So A times B minus C by using distributivity law is equal to AB minus AC. So as we have above AB equals AC, then this part equals to 0. So since A is not 0 and R has no divisors of 0, so then B minus A must equal to 0 or B equals 0. So then the cancellation law holds. We started with AB equals AC, then we ended up with B equals to C. For the converse, suppose the cancellation law holds and say A times B equals 0. So if A is not 0, so we can simply prove that B equals 0 by using the cancellation law in the equation. AB equals A times 0. So I took from the above equation AB equals 0. So the 0 on the right-hand side is equal A times 0, because in ring theory, if I multiply any element with 0, I will get 0. So then we cancel A from both sides, so we get B equals 0. Then if we have a ring with identity which has no divisors of 0, so the equation A squared equals A only has two solutions, which are 0 and 1. So otherwise, we might have too many solutions for this equation, A squared equals to A. So let's see what will happen if we have a ring which has divisors of 0. So let's look at the example Z6 again. So we see that 2 times 4 is congruent to 2 times 1 mod 6. The one of the left-hand side, 2 times 4 is equal to 8, but modulo 6 is equal to 2, which is equal to the right-hand side. But if we cancel 2 from both sides, we see that 4 is not congruent to 1 mod 6, because 4 minus 1 is not divisible by 6. So for the rings with divisors of 0, the cancellation law might not hold. Then what's integral domain? So integral domain is a commutative ring with identity which does not have divisors of 0. So we do have 3 conditions for integral domains. If I compare it with the definition of field, in field we say a commutative division ring is a field. So here there is a condition which is the ring has no divisors of 0. So the above example Z6 is not an integral domain because it has a divisors of 0. So the following are integral domains. So you see Z, Q, R, C has no divisors of 0 and they are commutative with identity. So then they are integral domains. As I said before, Zn, where n is prime, then is again an integral domain. So if n is not prime, like example above, so Zn will have divisors of 0. So where n is prime, so there will be no divisors of 0. Okay. If I have a ring R, so it's an arbitrary ring, it's not necessary to have an identity, which is not necessary to be a commutative, it's an arbitrary ring. So if we could find an integer n such that n times a equals to 0 for all a belongs to R. So the 0 on the right-hand side, when I say NA, so is the identity element with respect to the operation of addition. And NA means we add a n times. It means a plus a n times, which is equal to 0. 0 is the identity with respect to addition. So if we could find such n, such that NA equals 0, then we say that this ring is of characteristic n, where n is the least positive integer satisfying this property. Okay? If we cannot find such positive integers, then we say that R has characteristic 0. Let's look at a few examples. For the ring Z, Q, R, and C, there is no positive integer to multiply it to all elements in Z to get a 0, unless 0. So for Z only 0, I multiply to every element, I get 0. But for the ring of integers modulo n, so the characteristic is n. For example, if I take n equals to 6, so if I multiply all elements by 6 and then take modulo 6, then I will get 0 everywhere. So for Zn, the characteristic is n. How about the other rings? Let's look at power set of x with delta and intersection. So this ring has characteristic 2. Why? Because if I multiply 2 to a, which is the smallest positive integer with this property, 2a means a delta a. As I said in the definition, na means I add a n times with respect to the operation of addition. So the first operation here, we have delta. So a delta a from the definition is equal to a minus a union a minus a. So I can see both sets are empty, which is phi, then the result is phi. This phi is the identity with respect to the operation delta. So then this ring has characteristic 2. So actually, this ring is a Boolean ring. Maybe I will talk about it later. So maybe sometimes we find difficulty to find the positive integer to multiply to every single element of R to get 0. So there is a special case. If our ring has an identity, then we look at the smallest positive integer and to multiply to the identity is equal to R. So in this case, we only need to check the smallest positive integer n to multiply to 1 to get 0. So this n is going to be a characteristic of R. So here's a small proof. First, let's say R has characteristic n. By the definition of characteristic, then n times any element of R, we get 0. So in particular, n times 1 is equal to 0. So if I have some positive integer which is less than n and multiply to 1 is equal to 0, then I will get n times a by using this equation, because the ring has identity, n times 1 dot a equal to n dot 1 by associativity. As I said, R with the second operation is a semigroup. So n times 1 is 0, then 0 times a is 0. So this means that this ring has characteristic less than n, which is a contradiction. So for the converse, suppose n is the smallest positive integer with the property that n times 1 is equal to 0. So I have to show that this n is a characteristic of R. So just check, n times a is equal to n times 1 times a, because the ring has identity. So by associativity, this is equal to n times 1 times a. And we have, by the hypothesis, n times 1 is equal to 0. So 0 times a is equal to 0. So, and n, as I said, it's the smallest positive integer. So by the minimality of n for 1, then n must be a characteristic of R. So let's go back to the integral domain. What's the characteristic of an integral domain? So the characteristic of an integral domain, so it's either 0 or a prime number. So we don't have an integral domain with a composite number. So let's look at the proof. I will use theorem 7.20 to prove this theorem. So let's say we cannot find if we cannot find the positive integer n such that n times a is equal to 0, then R will be of characteristic 0. suppose there is such a positive integer and is not a prime. Okay, we do have n, which is not a prime number and is a characteristic of R. Then n can be written as a product of two positive integers. So from the definition of composite number. So n equals n1 times n2. As our ring has identity, because from the definition of integral domain is a commutative ring with identity. So by theorem to 7.20, n times 1 equals to 0 from left-hand side. So n equals n1 times n2, as I said, which is equal to n1 times n2, 1 squared. So then this is equal to n1 times 1 dot n2 times 2. So n1 times 1 times n2 times 1 is equal to 0. And our ring has no divisors of 0. Then must one of these is equal to 0. So either n1 times 1 is equal to 0 or n2 times 2 is equal to 0. But in this case, so if n1 times 1 is equal to 0, then the characteristic of R is going to be n1. But this contradicts the minimality of n, because we say the characteristic of R is n. So then n must be a prime. So in both cases, if n1 times 1 is 0 or n2 times 2, n2 times 1 is 0, so this contradicts the minimality of n. So the characteristic should be a prime for integral domain case. I would like to review the definition of ideal, and then I will try to connect the ideals with fields and integral domains. So as you know, for those who have taken the group theory course, so an ideal is a non-empty subset of R. So if I have I is a non-empty subset of R, then the triple I with plus and dot is called an ideal of R if I have two conditions. So if I pick any two elements in I, then their subtraction should belong to I. This is the first condition. This is actually the condition of the subgroup, because we do have R with plus is a group. So in group theory, we do have H is a subgroup, let me call it. If AB belongs to the subset, then A star B inverse belongs to the subset. Here I have A minus B because our operation is addition. So I can say B inverse equals to minus B. That's why A minus B belongs to I. The second condition is I should be closed under the multiplication of elements from R and elements from itself. So if I take any elements from R and any A from I, then their product, R times A and A times R, should belong to I. Because why R times A and A times R? Because our ring is not necessary to be commutative. So if R is commutative, so we only need to check one of them, because R times A equals A times R in this case. So let's see, if we do have a proper ideal of ring R, then no elements of R has a multiplicative inverse. So the elements in any ideal which has no multiplicative inverse. So as we denoted in the beginning, the set of all units in R will be denoted by R star. So it means R star intersection with I is equal to 5. So there is no common element between these two sets. So the proof we can do it by contrary. Let's say there is some element A which is not 0 and has a multiplicative inverse. We call it A inverse. So this inverse may be in R or maybe in I. So by the second condition, R is closed and the multiplication by elements of R, then A inverse times A should belong to I. because A is in I. So the result is 1. So this helps us to say for every element in R times 1 is in I. Then R times 1 is equal to R. So in this case, every element in R is an element in I. And we do have I is a subset in R, then I should equal to R. So this is contradicts the hypothesis as we said, I is a proper ideal, then I is not equal to R. Okay. There is a notion of a principal ideal. An ideal generated by a single element in a ring R is called a principal ideal. So likewise, we have in group theory, if we have a group generated by a single element, we call it a cyclic group. So here in ring theory, we do have an ideal which is generated by a single ring element, then this is called the principal ideal. So the elements in this ideal, which is generated by A, is actually a multiple of elements in R. So, which is quite different from the one in group theory. In group theory, when we say the group is cyclic, then all elements is a integral power of A. But here we have to multiply all elements in R, so we will get an ideal generated by A. So let's look at ideals in Z. So all ideals in Z are of the form n times Z. It means all ideals in Z are principal. So one can prove this by using division algorithm theory. So the proof is not so difficult. So what will happen if in a ring which every ideal is principal? So if every ideal is principal, then the ring is called principal ideal ring. We denote it by PIR. So if we check the ring Z as in theorem 7.26, it shows that every ideal in in Z, is principal. So the ring of integers is a principal ideal ring. So if I add one more condition to say the ring has no divisors of 0, so then the notion will be a principal ideal domain. So if R is an integral domain and every ideal is principal, then we call R is a principal ideal domain. So from this example, we can see Z is also a principal ideal domain. In this case, we can write simply PID as the abbreviation of principal ideal domain. Let's recall the definition of a field. As I said before, field is a commutative division ring. So it means this set F, so I use the letter F instead of R because I'm talking about field. So I take the first letter from the word field. So if F with the second operation is commutative, because from the previous definition we said R is a commutative division ring. So division ring means every non-zero element has a multiplicative inverse. So we do have identity with the second operation, we do have inverses with the second operation, then we will have a group. So then F minus 0 with the second operation forms a group. So in ring, we do have only the semigroup with the second operation. Now field, with the second operation, we do have again a commutative group. So here it means there is a relation between ring and field. So it means every field is a ring, but the converse is not true. Let's take this example. This one is different from the others. So let's take F, which is equal to the sum of A plus B times square root of 3, where A and B are rationals. So the operations in this case, operation of addition and multiplication, are natural. I mean, we add similar terms and we use distributivity law to multiply two elements of this form. So this is clear. R is a ring with identity. So the identity of this set is 1 plus 0 square root of 3 with respect to multiplication. And the identity elements with respect to addition is 0 plus 0 square root of 3. So only remains to show that every non-zero element in F has a multiplicative inverse. So let's have a non-zero element A plus B square root of 3. So if this one is not 0, then A and B not both at the same time is 0. Then A square minus 3B square not equals to 0. Why this part? Let me explain it. So A plus B square root of 3 inverse is equal to 1 over this element, A plus B squared. So I want to get an element of the form in F. I have to multiply and divide it by the conjugate of A plus B square root of 3. So I have to just change addition to subtraction. So by simple multiplication and using distributivity law, I get A over A square minus 3B square plus minus B over A square minus 3B square root of 3. So I can see the denominator is exactly the one I talked before. It shouldn't be 0. A square minus 3B square. So A over A square minus 3B square is a rational, and the second part is also a rational. So this element should belong to F. Then here every non-zero element have a multiplicative inverse. So then F with addition and multiplication is a field here. So we can see here Q is a subset of F, because like we extended Q by the part B square root of 3. So if B is 0, then I will get Q. What we have in field, if I take any two elements in F and AB is equal to 0, then must one of them is 0. So the proof is, if A is 0, so there is nothing to prove because the theorem is done. Suppose A is not 0. Okay? If A is not 0, so we can show that B is 0. Because we have a field, then every non-zero element has a multiplicative inverse. So A inverse is also in F, then A times A inverse is equal to 0. So we do have A times B equals to 0. So from this equation, we can say 0 equals to A inverse times 0. So the 0 by hypothesis is equal to A times B. By associativity, A inverse A times B. So A inverse A is 1, and 1 times B is B. So on the right hand side we have B, on the left hand side you have 0, then B is 0. Or one can try from the hypothesis to multiply both sides from left by A inverse and use associativity. You'll get B is equal to 0. This theorem tells us that field has no divisors of 0. Likewise in integral domain. So in integral domain is a commutative ring with identity which has no divisors of 0. So fields is also a commutative with identity and has no divisors of 0. So it means every field is an integral domain. So we need to think about the converse. Is every integral domain is a field? So here's a remark. Any field is an integral domain. So from theorem 7.18. But the converse is not true. So for example, the ring of integers is an integral domain, but it's not a field, because let's take 2 in Z. 2 has no multiplicative inverse in Z, because 1 over 2 is not in Z. So then what condition should be applied on an integral domain? We get a field. So we need to think about this. Look, if our integral domain is finite, then it's a field. So only finite integral domains is a field. Likewise, what we have in Zn, where n is prime, which is finite, I showed in both definitions, in field and integral domains, Zn is field and is an integral domain at the same time where n is a prime. So let's look at the proof of this theorem. Suppose the elements of R are A1, A2 to AN. So as I said, we have a finite set, then R is finite, so it has a finite number of elements. I call them A1, A2 to AN. Since we do have an integral domain, then it's commutative with identity. What I need to show is to show that every non-zero element has a multiplicative inverse. So let's take A is a non-zero element in R. So what I do, I multiply A to every element in R. I multiply A to A1 to A2 until AN. So I will get n products, A times A1, A times A2 until A times AN. So these products are all distinct. Okay, so if I say A times AI is equal to A times AJ, what I will get, because our ring has no divisors of 0, as I mentioned before, if the ring has no divisors of 0, then we can apply the cancellation law. So if I cancel A from both sides, I will get AI equals to AJ. Okay, but AI is not equal to AJ because I say these elements are all distinct. Okay, then the products are all distinct. Since our ring has identity elements, then one of these products should be 1. So I call it A times AI. As I said, 1 should be among these products. Then A times AI is equal to 1, and our ring is commutative with multiplication. So AI times A is also 1. So it means A has a multiplicative inverse, because A multiplied to AI is 1. So the inverse of A1 is A sub I. So this shows that every non-zero element of R is unit. Then R is a field. I hope the proof is clear. So the ring Zn integers modulo n, as I mentioned before, is a field if and only if n is a prime number. So this is the only finite field? No. We do have fields like with 4 elements. We do have fields with 9 elements. But this one is a finite field. I will talk about the other fields later in the part of polynomial rings, inshallah. So if our ring is a commutative with identity, then R is going to be a field if it has no non-trivial ideals. So if I take any ring and I look at the ideals, if the ring has only 2 ideals, which is 0 on itself, then this ring should be a field, like what you have in the above example, let me say, Zn, where n is a prime. So the only ideal of Zn, where n is a prime, is 0 and Zn itself, because the size of the ideal should divide the number n. And n is prime, the only positive divisors of n is 1 and itself. Also, in reals, the real numbers with usual addition and multiplication has only 2 non-trivial ideals, which is 0 and R itself. then as we know, reals is a field. And Q and complex is the same. Okay. Here I want to talk about the special type of ideal. So in terms of inclusion, okay, an ideal is called maximal. So in this definition, our ring is commutative with identity. So the ideal I is called maximal. The first condition is I should be a proper subset, not equal to R. And if I do have any other ideal between I and R in terms of inclusion, as I said, then this ideal should be the ring itself. So if we have another ideal, let me say J, and I is a proper subset of J, and J is a subset of R, then J should be the whole ring. So it means there is no such ideal between I and R. So in this case, I is called maximal. So let's look at some examples. So in Z, the ideal generated by 2. So it means 2Z, the set of even integers. So it's a maximal ideal. So there is no ideal in Z where the ideal generated by 2 is a subset of it. 3, the same, the ideal generated by 3 is also a maximal ideal. While the ideal generated by 4 is not a maximal ideal, because the ideal generated by 4 is a subset of the ideal generated by 2. So it means there is another ideal between the ideal generated by 4 and Z, where ideal generated by 4 is a subset of it. So one can see the ideal generated by 4 is not a maximal ideal. So what's the general form or the maximal ideals of Z? So the ideal, as I said before, all ideals in Z are principal. So the ideal generated by N is maximal ideal of Z, where N is prime. So for example, 2, ideal generated by 2, by 3, by 5, by 7, and so on. They are all maximal ideals. Okay? There is a theorem by Khasraw says, in a commutative ring with identity, every proper ideal is contained in a maximal ideal. So if I have an ideal, so if I have a proper ideal, then it should contain in a maximal ideal. What this means? This means that an element is invertible. I mean by element in a ring R, if it does not belong to a maximal ideal. Because as I said before, the elements in ideals are non-invertible. So if it's invertible, then it's equal to the whole ring R. So element is invertible if and only if it does not belong to a maximal ideal. Okay. So what will happen if I have a maximal ideal to the ring of quotients? So I think people are familiar with the quotient ring. So if our ideal is maximal, then the quotient ring is a field. Okay? Then, so out of a maximal ideal, we can get a field. Let's check the proof. So first, take a maximal ideal of R. I want to show that R over I is a field. Since our ring is a commutative with identity, then so is R over I. So what I need to check, I have to show that every non-zero element in R over I has a multiplicative inverse. So let me take A plus I to be a non-zero element in R over I. So from group theory part, we do have a theorem says A star H equals to H if and only if A belongs to H. So the negation of this statement, I have A plus I is not equal to I. It means A does not belong to I. Okay? Since our ideal is maximal, then I will consider the ideal generated by A and a single, the ideal generated by I and a single element A. So one can see that this I is a subset of I and A, the ideal generated by I and A. So since it's a subset, then this ideal, the ideal generated by I and A, should be the whole ring, because I is maximal. So it means the elements of R has the form I plus R times A. Because as I mentioned before, if I have ideal generated by A, the elements is the multiple of A by the elements of the ring R. And this sum, I is in I. So every element in R is of this form, I plus R dot A. As I said, our ring is with identity, then one is in R, then one should have this form. So I stated here, one is equal to I sub 1 plus R sub 1 dot A. This is for suitable elements in I and R. So from this equation, one can see that 1 minus R dot A, R1 dot A, this is equal to I1. And as we know, I1 is in I, then this element is in I. So this is equivalent to the theorem in group theory says, if A in H, then A star H equals to H. So then 1 plus I equals R1 dot A plus I. So by the operation of multiplication in the quotient ring, this is equal to R1 plus I dot A plus I. So 1 plus I is the identity of the quotient ring, R over I. So it means A plus I inverse is equal to R1 plus I. So this element has a multiplicative inverse. So hence R is a field. How about the converse if I have R is a field and to show that I is a maximal ideal? So let's check. If R is a field, and suppose we do have another ideal J between I and R, where I is a proper subset of J. So from this inclusion, one can see that there is some element in J which is not in I. So I say A in J and A is not in I. So it means A plus I is not equal to 0 plus I because A is not in I. So then A plus I is a non-zero element in the quotient. So and the quotient is a field, it means A plus I has a multiplicative inverse. So let's call the inverse B plus I. So A plus I times B plus I is equal to the identity in the quotient. So the identity of the quotient is 1 plus I. So from this equation, one can see 1 minus AB, because if I multiply these two cosets, I have to multiply the representative, A plus B is equal plus I. So it means 1 minus A times B belongs to I. And I is a proper subset of J, it means 1 minus AB belongs to J. But we have to remember A times B is also in J because A is in J. And if I multiply A with any element of R, the result is in J. So then I have to add these two elements, 1 minus AB with AB. So what I will get? I get 1. So it means 1 belongs to J. So in this case, as I proved before, J is equal to R. So I picked an ideal between I and J, and I got this ideal is the whole ring R. It means I is maximum. So let me explain this theorem by a simple example. So as I said before, the ideal generated by 3 in Z is maximal. Let's look at the quotient of Z by the ideal generated by 3. So by the theorem, Z over ideal generated by 3 is a field. Actually, this ring is isomorphic to Z3. And as we know, Z3, because 3 is prime, and I mentioned in the examples about fields, so Z3 is a field. So that's why Z over ideal generated by 3 is a field, because it's isomorphic to Z3. So there is another type of ideal called prime ideal. So let's have a commutative ring with identity, and let's pick an ideal of R. So the ideal I is called prime if the product of any two elements is in I, then one of them should be in I. So if A times B in I, then either A in I or B in I. So any ideals with this property called prime ideal. Let's look at the example. So what are the prime ideals of Z? So the prime ideals are those ideals generated by prime numbers together with zero ideal, because zero ideal is also prime ideal, and Z itself. So why zero ideal is a prime ideal? So if I take A times B in zero ideal, then the only choice for A times B is 0. And our ring has no divisors of 0, then either A is 0 or B is 0. So it means A belongs to the 0 set or B belongs to 0 set. Then 0 set is, so the additional multiplication is a prime ideal. How about the others if N is not a prime? Let's check the ideal generated by 4. So this ideal is not a prime ideal. Why? Because I can see 2 times 2 belongs to ideal generated by 4. But 2 is not in ideal generated by 4. Then this ideal is not prime ideal. Because from the definition, if A times B in I, and one of them is in I, then I is prime. But here, in this case, 2 times 2 is in ideal generated by 4, but 2 is not in 4. So also for the other composite numbers for N, so let me say N is equal to 6, we see that 2 times 3 is in ideal generated by 6, but neither 2 nor 3 is in ideal generated by 6. Okay, so the prime ideals in Z are those who are generated by prime numbers plus 0. So if we do have a ring with identity, a commutative ring with identity, then this ring is going to be an integral domain if and only if the 0 ideal is a prime ideal. So the proof is very simple. If R is an integral domain, then the 0 ideal is a prime ideal. If our ring has 0 ideal as a prime ideal, then the result is integral domain. So you only need to check the 0 ideal, which is a prime ideal, then you can decide whether your ring is an integral domain or not. So again, if I compare it with the quotient of a ring with a maximal ideal, I gain a field. But how about if I take the quotient of a ring by a prime ideal, then I get an integral domain. So if our ring is a commutative with identity, then an ideal is prime if and only if R over I is an integral domain. So we can do the proof by a similar way as I did it in the one about the maximal ideals. So let's have I be a prime ideal. So again, I will not check the commutativity and the identity element of R over I because it's simple. If R is a commutative with identity, then so is the quotient ring. So what I need to show that, I have to show that the quotient ring has a divisor of 0. So let's pick any two elements in R over I, which is A plus I, times B plus I equal to 0. I have to show that one of them, it should be a 0 element in the quotient ring. So from this equation, one can multiply these two cosets to get A times B plus I, and 0 plus I is A, so A times B plus I is equal to I. This is equivalent to A times B belongs to I. Again, this part is related to group theory because our ring with addition is a commutative group, and in a group, A star H equal to H found only if A belongs to H. Okay. Here I have A times B belongs to I, and our ideal is prime, then must one of B or A or B belongs to I. So either A belongs to I or B belongs to I. If A belongs to I means A plus I equal to I. If B belongs to I, it means B plus I equal to I. So it means this element is 0 in the quotient ring. So therefore, the quotient ring has no divisors of 0. How about the converse? Suppose the quotient ring is an integral domain, and I have to show that I is a prime ideal. So I have to take the product A times B in I. I have to show that one of them should be in I. So since A times B in I, then A times B plus I is equal to I from the right-hand side of this equation. So A times B plus I equals A plus I times B plus I. So the product of these two elements is 0 in the quotient ring. And our quotient ring is an integral domain which has no divisors of 0. Then must one of them is equal to 0. So either A plus I is 0 in the quotient, or B plus I is equal to I, which is 0 in the quotient. So in either case, if A plus I is equal to I, then A is in I. And if B plus I in equal to I, then B is in I. So this is exactly the definition of a prime ideal. So then I is a prime. Again, let's look at the example to explain the theorem. The ideal generated by 5 is a prime ideal, because 5 is prime number. Then Z over ideal generated by 5 by the theorem is an integral domain. Why? Because Z over ideal generated by 5 is isomorphic to Z5. And I mentioned before, Zn in general is an integral domain if and only if n is a prime number. As we see, 5 is a prime number. Okay. So what's the relation between the prime ideals and the maximal ideals? So one can see in a commutative ring with identity, every maximal ideal is prime, but the converse is not true. Okay, so if I check the ideals of Zn in general, of Z, let me say, sorry, every maximal ideal is prime. But the converse is not true. Why? Because I classified before the prime ideals of Z. The zero ideal was one of them. The zero ideal is a prime ideal, but it's not a maximal ideal. Because zero ideal is a subset of every proper ideal in Z. So what we need to think about, in which case the converse of theorem 7.44 is correct, or is halt, let me say. So if I have a principal ideal domain, so the converse is also halt for every non-trivial ideal. So if R is a non-trivial ideal, if R is the principal ideal domain and I is an ideal, then it's maximal if and only if it's prime. So I'll leave the proof of this. But so just what I want to say, thinking about the converse, is you need to focus on a special type of rings. So in this case, the principal ideal domain, for the principal ideal domain is okay, the converse is true. As we mentioned before, Z is a principal ideal domain. So if I remove the zero ideal and I say a non-trivial ideal, then it's prime if and only if it's maximal. If you see from the examples, ideal generated by N is maximal if and only if N is prime. Ideal generated by N is prime if and only if N is prime. So you see, they are the same. But if I remove the zero ideal, so they are exactly the same. Thank you for your attention. So I just finished the talk. If Prof. Nizam managed to.
Yeah, Dr. Sanhan, thank you very much for the topics. We open for any question from the students. There's also staff here. You can turn on your mic, unmute and ask question. Make sure you fill out the attendance form in the chat. I'll put it again. So we can email you the slide. Yeah, Dr. Sanhan?
Yes, for sure.
Yeah. No question from anyone? Okay, probably you want to collect and save the question for Wednesday after we email you the slide. Also, the class is very clear, Dr. Sanhan, with examples.
I hope it was understandable because
yes,
in terms, definitions.
Yeah, later on I will give some questions for assignment to my students in the class. So make sure they understand the one that you share.